Hello, everyone. Thank you for coming to our talk. We'll be presenting routing stateful AI workloads in Kubernetes, what's stateful in AI, where Kubernetes fails, and show some data. I'm Maroon Ayoub. I work at IBM Research. I lead the KV disaggregation SIG in llm-d, a project you'll hear about in this talk.
And hi, I'm Michey Mehta. I work on performance at RedHat.
Okay, so what you'll get today in this talk, you'll learn the single most important metric in inference in AI production. You'll understand why standard Kubernetes load balancing fails to deliver for AI inference. You'll understand what llm-d is and how llm-d solves this problem in a Kubernetes native manner. And you'll see real-world data showing how llm-d unlocks the potential of your hardware. We'll start with a joke. So two LLMs walk into a bar. The first orders a beer. The bartender goes, that'll be $3. The second says, same for me, but I'm paying cash. This joke captures part of the essence of what we'll be talking about. We'll dive into what paying cash means and why it's super important for inference. So we're starting with the 10x cost problem. What we're presenting really affects your bottom line inference production. Without these optimizations, you'll be pretty much paying 10x than you have to, and you'll be underutilizing your resources. So I'm starting with a quote from a Manus blog. Manus is an agent startup that popped a while ago. And in one of their blogs, they wrote, the KV cache hit rate is the single most important metric for production stage AI. It directly affects your latency and cost. And you really see this theme around in mainstream AI, such as OpenAI's, Anthropic, Google's. If you check the pricing pages, you can see for GPT-5, you pay $1 and a quarter per 1 million uncached tokens, and 10x less for 1 million cached tokens. The same can be seen in Cloud Sonnet and pretty much all mainstream AI pricing. And this talk will show you how Kubernetes or standard Kubernetes destroys these savings and why it doesn't work out of the box for AI inference. So some background to get the idea. The most important factor here is the KV cache. So what is the KV cache really? So to start there, I'll go over self-attention in high level. Self-attention is how transformers or transformer models understand context. Attention captures relations between different topics in different possessions in the input, like different paragraphs, relations between words and subwords. And it's a score that is computed between every two tokens in your input. So it's a quadratic operation. For 10,000 tokens, there will be 100 million of these operations. And this step is called the prefill step. It's what dominates time to first token, the time till you see the first token show up on your screen. And the solution for this problem is the KV cache. So instead of calculating KVs, keys and values, tensors at every step, you're reusing them when you're decoding new output tokens. So it's called KV cache, but it's neither KV, key value, or a cache. This is a good animation that illustrates this attention process and what KVs are. It's an animation from Hugging Face. On the top, you see the attention process for 4 tokens without KV cache. You see this growing matrix, which is required at every step, and every row or every tensors or data for tokens you already saw are exactly the same. In the bottom, you see the effect of caching, where you're only calculating the new data. You're reusing the tensors or the KVs from previous tokens, and you're only calculating the new ones. So with KV cache understood in high level, we'll move to VLM's magic, or how they efficiently manage the KV cache and what differentiates them pretty much, and the standard every other inference engine followed or developed in parallel. So 2 key techniques VLM has: paged attention, the manner in which they maintain the physical GPU memory. It's pretty much memory virtualization for GPU. And automatic prefix caching, which is responsible for the management and reuse of the KV cache blocks, utilizing some sort of prefix hash-based LRU map to maintain this information. But the bottom line is it's how VLM achieves this KV cache reuse and avoids recomputation where possible. And that's what really drives the TTFT gains you see across the inference stacks. A simple example showing inference over 10,000 tokens on a Qwen32B model shows the first time you're inferencing, you're paying for the full prefill. You're waiting 4.3 seconds. The second time when the KV cache is effective, it only takes 0.6 seconds, which is about 7 times faster. So we saw KV cache for attention and the forward pass, but in the wild, this KV cache or prefix cache reuse is pretty standard in pretty much most of the standard AI workloads. The first being conversational AI, multi-turn AI. So at every turn, you're adding a new question, and your context or your prefix cache is the entire conversation. If you don't have that ready in the KV cache, you're pretty much recomputing everything in every turn, and the waiting time will grow quadratically. The second being agentic workflows, standard agent. So the context or prefix cache reuse potential there is also the history or the steps history. So at every step, you have an accumulation of actions, tool descriptions, observations, and such. And every new step appends to that context. And reusing it is it's super important for practical agents, pretty much. So we now understand KV cache slightly and its applications in a single instance. And we'll talk about where Kubernetes or standard Kubernetes load balancing fails. So we talked about single instance and how VLM wins there, or the inference engines win there. But in production, you don't have a single instance. You have multiple instances, you have replicas, you have shards or ranks. And this once unified KV cache is now disaggregated. And if your load balancer is naive to that fact, is blind to the KV cache disaggregation, you're destroying these optimizations pretty much. A simple example, which is pretty much how all your requests will be served in a naive load balancing scenario, is where you've served a request on pod A, you have the KV cache warm there, you get to the next stage, the next turn in the chat, or the next step in the agent, and now your load balancer chose pod B to distribute the load evenly. You've lost the KV cache, you missed the warm KV cache, you duplicated the work, so now your second pod is redoing the exact same operations. Your user experienced increased latency for no reason, and you wasted your GPU resources. Whenever you're duplicating your prefill work, you're not doing decode. And this becomes the standard in your cluster with naive load balancing. So we established that the scheduler really needs vision into this disaggregated KV cache pool or states. And that's exactly what llm-d provides. So you get a real-time global view of KV cache across all your instances in a Kubernetes native implementation that builds on top of the Kubernetes Gateway API inference extension in what we call the llm-d inference scheduler, which implements precise prefix cache aware scheduling, as well as prefill decode disaggregation, which is out of scope. A high-level diagram on how the scheduler operates. So on the right, you see your VLM fleet. Each pod is emitting KV events. A KV event is fired every time a cache block is created or evicted on an instance. And this KV event stream is ingested or consumed by the efficient KV cache manager library llm-d provides, which consists of two main components. The KV events pool, which has the logic for consuming these events and index them or feeding them into an efficient index a KV block index, and a KV cache indexer, which exposes the API for querying this index efficiently, so that the inference or the inference scheduler is able to query it or use this API to serve requests. And the standard request serving flow looks like the following. So you query the KV cache index, you get a prefix cache affinity score, which is pretty much the percentage of the prefix already cached on your pods, which represents the computational work you're saving. We combine that with load-aware scoring, one that looks at VLM queuing, KV cache utilization, and other load metrics, and achieve a balanced scheduling strategy. It's very important to have the both, because if you're only using prefix cache affinity, you'll be overloading your pods. So with this scheduling strategy, you get balanced scheduling that ensures you're reusing prefix cache across the pods while also ensuring that you're using all your hardware. And with that, Michey will continue with some data.
Did you have one more slide? Okay. Okay, thanks, Maroon. So we're going to go over two different benchmark scenarios that we ran. This is the first one. This is we call it the shared system prefix benchmarking data. And so here, imagine there's 150 different companies. Within a company, you, let's say, always send a standard large prefix in. That's part of your company's protocol. You're going to send 6,000 tokens in, and then each employee within the company. Here, we've just modeled 5 employees per company of 150 different companies. So each of these employees will send 6,000 tokens in, plus 1,000 will be the question, and another 1,000 will come back. So that's sort of roughly the footprint of this particular workload. We ran this on 16 NVIDIA H100 GPUs. The model there is the Qwen32B. It was a TP2 deployment. So really, we had 8 replicas of this workload running. And essentially, if you do the math and look at all of the tokens that we've just talked about, it fills up, let's say, 3/4 of your available KV cache memory. But the important part is, if this is provided, you put this all in the right place, right? That you don't duplicate things. So theoretically, this workload fits. Now let's look at these charts. I don't know how well they're showing up on the screen there, but yeah, that looks pretty good. So the one at the left is TTFT, which is time to first token. It's a really important metric, right? You ask a question, when do you get that first response back? That's the one on the left. The one in the middle is what we call time per output token, right? That's each incremental token that dribbles in. How much do you have to wait for that token? And so the combination of these two kind of dictates what you see on the rightmost panel there, which is what is your overall throughput, right? How many tokens are we cranking out per second? Now, if you look at those lines, the bottom lines, remember the left 2 panels, the best thing you can do is get lower is better, obviously, right? So the bottommost line is the blue line, which is that's the precise prefix scheduler, and so that's doing really well here. You can see it's almost a flat line at the bottom. Maybe it's about 500 milliseconds for that line. Then the orange line, which is the approximate scheduler, is a little worse than that, but it's still, relatively decent. It's towards the bottom. And then you can see the other 2 schedulers are kind of the top. So let me once again explain these 4 lines. The precise scheduler is the one where not only do you know where everything went, but if let's say a particular question went to a particular replica, and then it got kicked out of there for some reason, right? It got evicted because it was running low. The precise one knows that, right? So it won't make the mistake of sending it there if it knows that it shouldn't be sending it there. The approximate one kind of just keeps track of where the last one went, which means that it could potentially get it wrong because it may think something is still in a replica even though it's been evicted a while back. The other 2 are random, right, which is where you literally do it randomly. And then the load-aware scheduler, those are the 2 lines at the top that you see. Those are more where it's looking at load metrics, like, okay, how busy is each replica in terms of, is there queuing there? or how much is in the KV cache, right? Looks at a couple of metrics to do that. But you can see the clear differentiation there in the TTFD line. And then for this particular workload, the teapot, the middle panel, they roughly track equivalently across these 4 workloads. And then for the one on the right, which is just the throughput, once again, you see what we would hope to see, which is that the orange line is doing very well. And the blue line is doing even better, and the other 2 are kind of more towards the bottom. So just 2 more views of this particular data for the same workload that we talked about before. Here we're showing you, every time you ask, a prompt comes in, ideally you have landed on a replica where you already have that particular prompt sitting. So we're looking at the prompt, the effective cache throughput, which is literally how much did you get for free, right? How much did you get out of that replica without having to do a lot of work? Because as Maroon showed earlier, it's like 7 times cheaper to pull it out of your cache rather than doing all of that expensive computation all over again. So once again, we're seeing trends here, which are what we would like to see. Precise gets the most number of tokens directly out of the cache. The approximate score gets a little less out of the cache. And then you can see the random one really doesn't manage to get a whole lot out of the cache. Because remember, we've got 8 replicas here. So chances are you may have sent it to the wrong place where the question that you previously asked is no longer sitting there. Similar pattern here. This is a really important metric, which is there's always queuing in a system, right? I mean, you're going to have a little bit of queuing. And here, this shows the magnitude of the queuing. And you can see that it's the right direction. Precise, the queuing looks a lot better than all the way on the right-hand side, where that's the random scheduler where there's quite a lot of queuing. OK, this is now what we talked about before was like a single large system prompt that is shared among multiple users in an organization. This one is more a conventional chat kind of workload, right? So you're asking questions, you're getting answers, you're asking questions, getting answers, and the context keeps growing over time, right? So for this one, we're using essentially a context. So the initial prompt is 10,000, and then we go back and forth 5 times, sending 1,000 in, 1,000 come back. Then everything goes back out, and you get. So this is just any kind of a chat workload that you've all used before, and you can see those. If you look at the quadrants there, the leftmost one are the metrics for the load-aware scheduler. The right one are the metrics for the prefix-aware scheduler. And I just wanted to call out one thing in all of this data here, which is if in each quadrant, if you focus on the top left, that's really how many prompt tokens are you processing per second versus how many of the ones that you process came out of the cache. So similar to what I showed you for the previous workload, here we've got them both superimposed. So you notice for the load-aware scheduler, you can clearly distinguish the yellow and the green lines, which means that there was a gap between what it asked for versus what it got. And that gap represents real GPU work being done. On the right-hand quadrant, if you look at that equivalent chart, you can't even see the yellow line. It overlays the green line so closely because virtually all the tokens that it's asking for are coming out of the cache. So it did a really good job putting stuff in the right place and then pulling it out of the cache. OK, so we've gone over lots of different ways of doing the scheduling. And let's just quickly recap what the 4 methods were, right? So first is, you all know this, like random. You just pick some of these 8 replicas or whatever number of replicas you have, and you're done, right? You just send it there. Load-aware takes you 1 degree better, right? You're saying, OK, is there queuing? If there's queuing, I won't send it there. I'll send it to the pod that looks least busy. That's one metric. The other one in load-aware scheduling is you would look at, OK, is his KV cache is it 60% full? Is it 70% full? because you may not want to send it to a KV cache that's really using 80 or 90% of the place. You may send it to some replica that has more KV cache available. Next, we move to approximate previous caching, which is where you say, okay, I will send it to the last place that I know I sent this prompt. It may not be completely right, but it's a pretty good guess, and in fact does better than the load-aware strategy that I just talked about. And the final one, the holy grail, is really the precise one, right? Because you know exactly if it's there, where is it? Let me send that question to the precise replica where we know all the KV cache for this particular question is sitting. Okay, so I've gone over lots of data here, but really the most important data is your own data. It's your benchmark, the workloads that you are going to run. So here for llm-d, that link is for what we call the well-lit paths. These are the paths where we carefully enumerate for you step by step how to run these workloads. And so if you go to this place, you will find one well-lit path for approximate. It's just called Inference Scheduler, and that's the approximate one. There's another well-lit path for the precise prefix scheduler. There are others there, but these are the two that we're focusing on for this particular talk. Okay, so let's wrap up with the key takeaways. First of all, as Maroon talked about right at the beginning, AI workloads are stateful, right? When you run something, it's leaving some debris behind in the replica where that question went. So you really want to send prompts to the current location. So it's really stateful in that sense. Traditional routing that we do would not be aware of this issue of where is the state that you really care about. That's why we have all the stuff that we just talked about. And so llm-d is something that makes Kubernetes AI aware. So thank you all for coming for this talk, and we're now open for questions. Put another one forward, right? No. Okay,
Questions? You're all convinced KV cache is super important.
Yes. I think the question was, do we persist the cache data, or is it only sitting in memory? In the work that we're talking about here, we do not. But in theory, you can take the KV cache and push it out to main memory if you don't have, if you want to just keep switching back and forth between main memory and GPU memory. And then there's also connectors available to actually store it onto persistent storage. But that's not part of the project right now.
I'll elaborate on that. So in llm-d, we do have KV cache offloading. What you're referring to could be called KV cache offloading. We have offloading to CPU memory, so that extends your instance's memory. So the HBM or the GPU memory is kind of very limited. So you can tier the space or increase it with CPU memory. And we also have storage offloading. So you can offload to persistent storage or local storage or shared storage. And there are trade-offs and use cases where you switch these on and off. CPU offloading is a no-brainer. You get a lot of CPU on all your nodes, so you can make use of that. In terms of persisting KV caches, so these are, you're extending the memory, but whether you want to keep these KV caches in or not it depends on the workload. We have some data on that in the llm-d website.
Is there any advantage to the randomization, the cache hit rate is less? Does that affect the answers that the LLM is producing, or does that make sense? If you cache everything, and so the LLM has learned that pattern, so it will produce a similar set of answers every time.
Yeah, so this is a very good question. What you're referring to is semantic caching, where the model or your system remembers answers and may reuse them for different or similar questions. But again, the KV cache, the name is very confusing. It was chosen by ML people. So it's neither KV in the standard sense or cache. It's really the state you need in your GPU memory to generate the next token. And for the same inputs, the same exact inputs or prefixes, it's exactly the same KVs. And that's why you cache them. But you really need the state in order to generate more. So what really affects the output is maybe the temperature and randomness in the generation, but the KVs really need to be there as is every time for every same prefix.
Okay, thank you.
Is there any logic around invalidating or sort of when you know to drop it, or sort of, user logs off, it's not worth keeping it around anymore? What's the thinking behind some of that?
Yeah, so today it's, so we refer to VLM, and I think it's standard pretty much everywhere. The KV cache memory is managed in an LRU manner, so KV blocks come in. If there's no space, you evict the least recently used. But we are looking in llm-d at making that more efficient, so maybe cost or context-aware LRU management, so you send a prompt. Today, all the blocks or chunks are treated the same. But if you know that this part is a system prompt and this part is a unique, maybe something that will never repeat portion of the prompt, then you would want to treat them differently. And we are looking into exposing APIs for granular and explicit KV cache management so that you as a user can define whether this is important to cache or your prompt is important to cache or it's a one-time thing. But today it's an LRU cache management pretty much across all the tiers.
Hey, thank you for the talk. I had a question about routing, because so you're doing this when the request comes in, and I was wondering if there's a possibility that we end up routing a lot of decode heavy requests to the same instance because we don't know how many tokens will be generated. So if we are doing prefix cache matching, we route requests to instance A, but all of those requests generate 2,000 tokens. So we end up out of KV cache. And so how we can handle that?
So that's also a great question. There is the prefill decode disaggregation optimization that we also provide. It was out of scope for this talk, but it would help you sort of manage these kinds of workloads. So your decode instances would be optimized and you'd want them to do just decode. So prefix cache hits only help you there. And prefill instances would be optimized for prefilling, and they'd still do that best. But we are looking into trying to predict the decode length or estimate like how much you'd get, and that would definitely help with better scheduling.
Also, does llm-d also do autoscaling?
Autoscaling, there is support for autoscaling. It's in very early stages, but it's something we're actively working on.
All right, thank you.
When you're using a distributed cache, like LM cache for distributed inference, would you then kind of focus, instead of doing the precise scheduler, would you look more at like your queue depth and other metrics to make that load balancing decision?
Yeah, so the disaggregation or the distributed cache here comes naturally from spanning up multiple instances. We don't actively try to disaggregate it or split it. You would have intentional disaggregation in maybe tiered caching where you have remote storage, say, for example, across your node. But the disaggregation or distribution here is really that you naturally have multiple pools of KV cache since you have multiple instances. And you're trying to be aware of this disaggregation so that you don't duplicate KVs across these otherwise isolated pools.
Okay, thanks.
Okay, I think we're on time. Thank you, everyone.
Thanks, everyone, for coming. Bye-bye.